All right, let's talk about limiting reactant and what this is. This is where things get a little bit more complicated with our stoichiometry problems, and you'll see why. There's a lot to keep track of, and there's a lot of mistakes that can get made along the way, and you just have to be very detail-oriented and pay close attention to the work you're doing as you solve these problems. Okay, let's first talk about what a limiting reactant is and is not. So in questions that we've answered so far in class, they've looked like this. You know, a certain amount of grams of copper sulfate reacting with excess lithium nitrate in a reaction. So in this example, you can see that we've only got one amount of a reactant, and the other reactant is in excess. And what we've done so far is just assume that the amount that we've been given in the problem is going to lead to how much product we can make. And that's how limiting reactant works as well. It's just that limiting reactant is a little bit different because we're not given a defined excess reactant. We actually have to find that. So in a limiting reactant problem, the mass of the reactants is given. All of the reactants, usually there's only two of them, but if there are more, all of the masses are given. Okay, you have to figure out what the excess reactant is and what the limiting reactant is, because the production of any product is totally dependent on the limiting reactant. And let's talk a little bit about limiting reactant with a simple example here. So let's just say, get this stuff out of here. Let's just say that the recipe for the world's most pathetic sandwich is 2 slices of bread and 1 slice of cheese gives you 1 delicious sandwich. Okay, and that is, we cannot budge from that recipe. Okay, so let's just pretend that we were given 30 slices of bread and only 2 slices of cheese. The question is, how many sandwiches can you make? And you can probably do this in your head. You know, if one sandwich is 1 piece of cheese and we only have 2 pieces of cheese, then obviously we're gonna use 4 of our bread slices and have a bunch left over. But what you're really doing is asking a question like this. If 30 slices of bread were to be used, how many pieces of cheese would you need? And so basically you're saying, well, if 30 slices of bread are used and the ratio of bread to cheese is 2 to 1, then we would use 15 pieces of cheese. Okay, and clearly comparing the amount of cheese that would be required to use up all the bread is not nearly enough because we've only been given 2 slices of cheese. That's the kind of work you're going to do in these limiting reactant problems. Okay? All right. So let's look at a scenario here. 454.62 grams of potassium phosphate reacts with 398.55 grams of calcium sulfate. Double replacement reaction. How many grams of each product are produced? Okay, so obviously the first thing you always need with this kind of work, as with any stoichiometry problem, is a balanced equation. And here it is. And I've already written down the molar masses of these compounds, and you can save yourself, well, it doesn't really save you any time, but I think it's more convenient if you just go ahead and calculate each of the molar masses before you really get started with the problem. You know, you're gonna use them, and it's kind of nice just to have them directly under the chemical formula for reference. Okay, so we'll come back to this problem pretty frequently here. So first step here is to figure out which of those reactants limits the production of the product. And here what you're really asking yourself is, if all of one of the reactants reacts, how much of the other reactant would be needed? So, like, for example, if we wanted to consume all of the potassium phosphate that we've been given in the problem, we want to make all 454.62 grams disappear, how much calcium sulfate would be required to make that happen? right? So that's the question you're asking, and you can do them either way. I always just start with this compound and see how much of that is required. Okay, so here's how you make that happen. We're going to do a stoichiometry problem, gram to gram, between the two chemical reactants. Okay, and so one of them is A and the other one is B. And just, I think for consistency's sake, I always make the first one A and the second one B. That way I'm always doing it the same way and showing you the same way. And anyway, that's how I'll do it. Okay, so that question then is this. If all of the potassium phosphate reacts, how much of the calcium sulfate is going to be needed to make that happen? Okay, so this is where we're going to set up our gram to gram stoichiometry as we've done in the past, where given grams of A is the amount of potassium phosphate, and then we're going to see how much B, not is produced, but how much B is needed to react with all of the A. Okay, and here's what that math looks like. So here's our starting amount of potassium phosphate, molar mass of potassium phosphate, mole ratio between potassium phosphate and, what's the other compound? Oh yeah, calcium sulfate. I'll put the equation here so you can see it. So the 2, this 2 is that 2, and this 3 is that 3. Okay, and then this is the molar mass of the reactant B. All right, and it turns out that to react all of the potassium phosphate, it would require 437.39 grams of calcium sulfate. Okay, so if it takes a certain amount to get rid of our first reactant, then we can compare the amount of calcium sulfate given to us in the problem with the amount of that calcium sulfate that's going to be required in the reaction of all of the potassium phosphate. So we've been given 398 grams, and it's going to take 437 grams, right? So clearly it's going to take more of that calcium sulfate than we have to give, and that makes it the limiting reactant. And so here's a little recap of that. So this is the amount that we just calculated. 437.39 grams of calcium sulfate are needed to react with all of the potassium phosphate, but we've only been given 398.55 grams of calcium sulfate. So here's a little rule of thumb. If more of chemical B is required than is given in the problem, then B is the limiting reactant. That's what happened to us in this problem. We had more of the chemical required than has been given to us in the problem. It could have gone the other way. Like if, for example, we had calculated this number to be like 200 or something like that. If we had calculated that 200 grams of calcium sulfate were needed and we'd been given almost double that in the problem, if less of chemical B is required, then that means that A is the limiting reactant, okay? And the whole reason that we find limiting reactant is because the limiting reactant and its quantity in grams is used to calculate the amount of product that gets produced in the reaction, okay? Okay, so now that we know what the limiting reactant is in this problem, we can actually go back to the problem and remember that this question is asking us how many grams of each product get produced. And again, we have to calculate those yields based on how much limiting reactant we have to go around. So we just do some stoichiometry here with the same gram to gram stuff, where now our limiting reactant is always used as chemical A. So I'm gonna write that down so you have it. Limiting reactant. Okay, we always use limiting reactant as chemical A in the production of our compounds. So remember, we're asking about how many grams of each product get produced, and so here's the math on that. I'll keep the equation up here so you can see what's happening. So this first calculation shows the theoretical yield of our potassium sulfate. So we have determined that calcium sulfate is our limiting reactant, and so we have this 389. That's from the problem here, right? That's the amount of limiting reactant we're starting with. Its molar mass, its mole ratio, and then here the mole ratio is the coefficient 3 and the coefficient 3 for potassium sulfate, and then the molar mass of potassium sulfate. So theoretically, based on our limiting reactant, we can make 510.14 grams of potassium sulfate. Okay, we're asked about both of the products, so here's the math on the second product. And again, we're using the same setup basically because it's the same limiting reactant. So the first part of these two problems is pretty much the same. And so for the second product, which is calcium phosphate, we're going to have a different coefficient here, the 1 that comes from the calcium sulfate, and a different molar mass. And it turns out that based on our limiting reactant of calcium sulfate, we can produce 302.66 grams of calcium phosphate. Okay. Now, another question you might be asked is, how many grams of the excess reactant are left over? And so again here, what you need to do is basically figure out in a gram-to-gram Stoic problem, comparing both reactants again, sort of like you did in the first part of this problem to find the limiting reactant, we're gonna compare our reactants. Now, in this case, we gotta make sure that the limiting reactant is A, okay? And the other reactant is B. So the question really is, how much of B gets used if all of A reacts? Okay, and here's the math on that. So we'll go back to our starting amounts of stuff here. So here's our limiting reactant again. It's coefficient here of 3. This time though, we're comparing it again to calcium phosphate, and its molar mass is here. And so what we're basically saying here is that if you reacted all of your calcium sulfate limiting reactant, 414.25 grams of potassium phosphate get used. And of course, that's less potassium phosphate than we start with. We start with this amount, 454.62. But now that we know how much of it we started with and how much of it got used up, then we can just subtract those values. This is the starting, this isn't the ending, this is like the used, the amount used. And then we get that 40.37 grams of that potassium phosphate are leftover and unreacted. So, lots to keep track of, but practice makes perfect, and we'll do a bunch of these in class.